Friends, welcome you all to this class of uniform flow in mobile boundary channel. In the last few classes, we have discussed about uniform flow, various aspects of uniform flow, but all those that we made those discussions were on rigid boundary channel. That means when the channel boundary is fixed. By boundary here we mean that either the bed or the bank, everything is fixed. So in that context only we were discussing uniform flow. Now today class will be basically concentrating on the issue that if the channel boundary is not fixed, it is mobile, like say in a river it can happen, particularly when the river is flowing through a alluvial soil with say fine sand or maybe little coarser sand, but still suppose the water can erode that sand, then there can be change in the bed form. And then similarly, suppose if we talk about man-made canal also, say in irrigation canal, we can have a sometimes due to economy, it may not be possible to provide a lining to all those channels. Say in field level channel, it may not be possible. Suppose for irrigation, in the main canal, it may be possible to provide a lining, but say the minor canal or the distributaries or that is going into the field which is ultimately carrying the water, it may not be possible to provide a lining. And if the soil type is of the type that it get eroded or the water can erode it, then this make a different cases of uniform flow. Basic concept is same, but we need to see whether all the theories that we applied for rigid boundary channel, all the formula, whether we can apply those as it is or we need to consider some special issues in that. Well, before going to this, we have done in the last class say uniform flow that we have discussed very clearly. Well, let us recapitulate what we did in our last class. Well, we studied uniform flow, that already I have explained the how uniform flow occur and all these things we have studied in the last few classes. Then of course we did uniform flow computation in rigid boundary channel, and then we also studied that mobile boundary channel there can be scouring and silting. This when mobile boundary channel is there, in our very introductory class and in subsequent classes also we have discussed that there can be scouring, there can be silting. Now our point is that should we consider these factors in analyzing uniform flow? Well, now before going to various expression, various relation of forces and that influences the flow in mobile boundary channel, we need to know some of the fundamental relation that when the water flow, then how the water exert force on the bed or what sort of stresses get developed in the bed. And that is why what I feel that some of the prerequisite that I feel that is necessary before studying the mobile boundary channel we will be discussing first. Well, then one of that is that expression for the bed shear stress tau 0. Now you can concentrate to the slide that we generally use the symbol this tau 0 for the bed shear stress. Well, now what can be the expression for this tau 0? Bed shear stress means when the flow is moving, then how much shear stress the flow is exerting on the bed, and then for that in uniform flow how we can have the expression for this tau 0. Well, now let me take a simple channel like this and say uniform flow is flowing. Now we are concerned about uniform flow. Okay, channel section may be anything like that, but it is flowing uniform flow. Okay. Now if we take two section, 1 and 2, and if we recall the expression for our momentum, and rather if we write the momentum equation, then we can write that what are the forces acting on this water, what are the forces acting on the section, the water between existing between the section 1 and 2. Well, that we can write first, say the force, the pressure force working in this direction, and if say x bar is the distance up to the center, then this pressure force we can write that gamma into x bar, or sometimes we write this as rho g into x bar, that is the pressure at that point multiplied by the area, we get the pressure force. That way some pressure force is acting from this side, and another pressure force, I mean in this body, the pressure force on the from the downstream side, that will be say P2, and weight of the liquid, that is W, and then component of this weight which is acting in this direction, that is in the direction of flow, is W sin theta. In fact, this sort of forces we have written several times. Now, normally we used to write earlier that this force, that is the resisting force that is acting on the that is opposing the flow, as say Ff. Now, here we will be writing it in a different term, that is say tau 0. If tau 0 is the shear stress, then if we consider that tau 0 is the average shear stress, means shear stress in the bed at different point, in reality it can be different, but say we are assuming, and on the side also it can be different, but let us assume that this is this can be considered uniform shear stress, and then if this is the perimeter and if this is the length, then we can write that shear stress or this force, resisting force, is equal to total surface area is equal to perimeter multiplied by the length and multiplied by the shear stress. So, this is the shear stress which is generated here and is opposing. Actually, frictional resistance, when the flow is moving, always we know that opposing force will be just be sufficient to just obstruct the flow, and that way this tau 0 is, we are writing that bed shear stress, and it will be the force generated will be proportional to this tau 0, and it will be equal to rho into L. Well, now this force, what we can write, say total force, and suppose the Q is the discharge moving, in this direction. Then we can write the equation as, say P1 is the force from this direction, then minus P2 is the force from that direction, and then plus W sin theta, then minus tau 0 into P into L. These are the forces that are acting here, and this is equal to rate of change of momentum. Now, we know that when we talk about momentum, we need to put the momentum coefficient when we are writing this in terms of average velocity. So, Q we are writing say as A into V or whatever it is. So, we will be using the momentum coefficient B, and let us write it as Q is the discharge flowing, then multiplied by rho is the mass, and the change in velocity say V2 minus V1. So, ultimately this expression is giving us the rate of change of momentum, and that way these are the applied force and these are the rate of change of momentum. Now, this expression we have written earlier also, just to refresh our mind and to write it in the form of tau 0, we are writing it again. Well, now this is a case of uniform flow. Now, when we talk about uniform flow, our depth is same. Suppose whatever depth we are having here, whatever depth is here, these two are same, means section 1 and 2 depth are same. Now, if this depth are same and if the channel is prismatic, that is this section and that section we are having, that is section 1 and 2, our sectional area is also same. Then this pressure force from the upstream side and pressure force from the downstream side, these two will be equal, these two will be equal. And similarly, we know that in uniform flow this V2, that is the velocity at the section 2, and the V1, that is the velocity at the section 1, will be again equal. Well, that way what we can see, that if this V2 and V1 are equal to 0 in uniform flow, so this will become 0, and then if this P1, P2 are also equal, then we can simply write that W sin theta minus say tau 0 into PL equal to 0, or these two we can just equate like this, that is say W sin theta is equal to tau 0 into P into L. Okay. Now, what is this weight? The weight is, already we were drawing several times, this weight is nothing but if the unit weight of the fluid is say W, or sometimes we write it as rho g. Rho g is the unit weight of the fluid, sectional area is say A and length is L, then this is the total weight of the fluid. Okay. And then that is why here we can write it as W, we can write it as rho g A into L, and sin theta, this is equal to tau 0 into P into L, tau 0 into P into L. Okay. Now, this sin theta, again for small value of theta, what we can do, for small value of theta, we can always write sin theta equal to tan theta equal to theta. So, that means this is equal to the slope S, fine. And then this equation we can again write in the form that rho g, L and L would get cancelled. So, A into S is equal to tau 0 into P. So, from this what we can write, that our basic objective is to get this tau 0. So, tau 0 is equal to, you can write rho g, then A by P into S. Now, this A by P term, we know that it is nothing but the hydraulic radius of the open channel. So, we can write that tau 0 is equal to rho g R into S, and many a time this rho g we can write as W R S. W means this is unit weight, sometimes it is written as gamma also. So, any symbol can be used, W R S. So, that is what our tau 0 expression for the shear stress. And then using this expression for shear stress, now this is the very basic expression which we will be using for finding, that is, if the stress is more than certain value, then there will be erosion. If the stress is less than certain value, then there may not be erosion or scouring. And this shear stress, again we can write it, we can express a different value, like that is tau 0 by rho, and then if we take a square root of that, this particular expression is said as U star, is written as U star. What this is? It is called shear velocity. You can see it is root over tau 0 by rho, means we are getting root over g and root over rs. Now, again the velocity formula also we know that root over rs comes. So, it is in the similar form, and then each unit is also similar to velocity. So, it is called shear velocity. Okay. So, with this first introduction to shear velocity, now we can go to another important parameter or another important understanding of the shear force. Now, shear force or shear stress on the bed is one issue. Then again another issue is that whether the bed is smooth or rough. Means when the erosion process start, that is in the mobile boundary channel, suppose the erosion process is starting, then there may be some undulation in the bed, and otherwise also of course it is a general in general term also there will be some roughness in the bed. Now, that roughness, how much it is rough, whether it is smooth, that is very relative terms, that is very relative term. Say one can say this is rough, another can, for another person it may be smooth. And when we come in the context of water, say in a river bed there may be some undulation, and then suppose depth of flow is very high. Now, for that high depth of flow, a smaller undulation may not be considered as rough, but say for a small depth the same undulation of the bed may be considered as rough. Similarly, suppose bouldery river is there, there is a size of the boulder, and that size of the boulder, whether we call this as a rough bed or a smooth bed. Well, there also again that question come, if basically the point is coming in the form that if that roughness is not creating turbulence in the main flow, that roughness is not going into the turbulent zone and creating turbulence, then we refer this as a smooth. So, I mean there is a specific definition of smooth and rough boundary when we talk in terms of hydraulics. So, we call that as a hydraulically smooth and rough boundary. Well, so you can now concentrate into the slide again. We will be just drawing how we can define this hydraulically smooth and rough boundary. Well, that basically when we studied, probably you have studied already, or we have seen in our fluid mechanics also, that when a flow is coming from this side and say it is moving over a boundary. Now, in channel of course this is always a boundary, I mean our bed itself is a boundary. So, when it is moving over a boundary, then the flow get retarded near the boundary, and so the zone where the flow is getting retarded is increasing like that. Say in this portion the flow is retarded and then it is going up to certain extent. Then in this portion the flow, as it is getting retarded, and the flow will be laminar in this portion, and then it is moving like this. That means this is extending, the zone of influence that is extending, and then here the flow may be turbulent, flow will be turbulent, and then but still we get a layer here below which, that means in this portion the flow is still laminar. So, that layer which is, suppose a flow is turbulent, in general flow is turbulent, but under the turbulent flow there is a layer which is again continuing as a laminar. So, that suppose depth if I write as delta dash, then it is called laminar sublayer. So, this layer is called laminar sublayer. Now, in open channel flow, say let us consider there is a up to infinite extent there is the channel bed, and it is coming from this side also there is a continuation of the channel bed. So, we are concerned about this part only, that is we know that there is a laminar sublayer, there is a laminar sublayer. Okay. And of course, this expression for laminar sublayer is also given by different experimental study, and this is can be written as U star like that, 11.6 U star. Well, this laminar sublayer has something to do with the roughness. Now, let me draw one boundary, say this. Okay. Now, this boundary may have some roughness. This boundary may have some roughness. Again, as we understand that when we talk about a roughness in a boundary, it is very difficult to say or very difficult to define let's say roughness, if I write as some value k, suppose roughness is, or we can use a suffix ks, say surface roughness k, then definitely the roughness at different area will be different, and exactly defining a diameter or dimension of that roughness is very difficult. And that is why we use a term that is called equivalent sand grain roughness. This roughness can be expressed in terms of equivalent sand grain roughness, Ks. Well, what we mean by equivalent sand grain roughness, equivalent sand grain roughness, that information is also required. In fact, Nikuraj says he conducted experiment. So, Nikuraj conducted experiment with different material, say he did use different material and say making pipe, and then he found he was observing how this material is behaving, say maybe head loss, how it is, how the head loss is occurring there, and then he did use different sand grain, collected different sand grain, and say of uniform size sand grain he was collecting, and then he took the similar diameter pipe, and then the inside of the pipes were coated by different type of sand grain, means different sizes of sand grain. Say one pipe is being coated with a very fine sand grain, another pipe is coated with a little coarser sand grain, and so that way now for those pipe where it was coated, for those pipe which were coated rather with known sand grain that are known, that is this pipe is coated with this sand grain, means its roughness is the diameter of that particular sand grain, and diameter of that particular sand grain is known. Now he conducted experiment with those pipe and the pipe of different material. Then he found that yes, this material is behaving similarly to the material, to the pipe coated with a particular size of sand grain. So now he has two things in his hand. One is a particular material of the pipe, another is a pipe coated with a particular size of sand grain which are behaving in the same way. So then for that particular material, suppose steel, for the steel he has a in his hand with a particular type of sand grain. So he said that this has sand grain roughness of this much. Well, so that way for different materials sand grain roughness were given, and then for a particular material we can consider this Ks. Of course, on principle or in general we can say that this is a roughness. Suppose for some material there can be where we may not have this sort of value. Now this is the roughness, you take it like that, this is the roughness, and say the laminar sublayer depth is suppose here is the laminar sublayer depth. Okay, say this is the laminar sublayer. We generally go from the average height, average of this thing. So this is the laminar sublayer height and depth, and this is say delta dash. Now if this Ks is very small as compared to this laminar sublayer depth, then we call this as a smooth. Now again in engineering, if we say very small, these are sometimes become vague. So we need to express it in terms of some definite value. Well, that definite value was given as if Ks divided by say delta dash, if this is less than equal to 0.25, means delta dash is say 4 times greater than this Ks. If it is less than equal to 0.25, then we call that particular surface as smooth surface, that particular surface as smooth surface. Well, that means there is another point, important point, that it is not only the flow depth, but the depth of laminar sublayer, and this depth of laminar sublayer will depend on this U star, that is shear velocity. So that way, and viscosity of the fluid. So all this factor will influence, and finally we are getting that a particular surface can be considered as rough for a situation, and for another situation the same surface can behave as a smooth also. So, it is always dependent. Now, this, if this is the value, then we can call this as a smooth boundary. Smooth boundary. Smooth means hydraulically smooth. And then if we have that value, that Ks by delta dash, say another case, here say roughness are very large, okay, and this is our roughness Ks, and then if I calculate the say delta, this is smaller than this, delta dash is smaller than this. That means the roughness will move into the, or rather roughness will penetrate through the laminar sublayer, and then it will go to this turbulent layer. This part is turbulent, this part is turbulent, this part is of course laminar, this part is laminar, and this is going laminar, and that laminar portion which is remaining below turbulent we are naming as laminar sublayer. Well, so this roughness when it is moving or when it is going inside the turbulent, then this will influence this sort of flow. When the roughness is going like that, then this is influencing this sort of flow. Otherwise, if it is not going into the turbulent zone, then whatever rough it may be, it is not influencing this flow. So, that way this flow will be behaving as if it is moving over a smooth surface, and that is why we call this as a smooth. Now, when this value is greater than equal to 6, that is Ks is 6 times larger than the delta dash, laminar sublayer depth, then we call this as a rough. Well, so we have got the smooth, hydraulically smooth boundary and hydraulically rough boundary. Then in between there can be always transition, like that if it is 0.025 less than equal to, say we can write Ks by delta dash, and it is less than equal to 6, then in between this part we will call that the boundary is in transition. Now, why we are talking about all this rough, smooth, and what is our basic objective? Basically, we will start with some derivation of equation, and this in this derivation we will have to use some approximation or some theory that has come from observed value, and say those relation will give us some relation which are valid only for smooth, some relation which are valid only for rough. So, we need to know what is basically smooth and rough, and on which these things will be valid, and because of that we are starting with this and just introducing what is hydraulically smooth and hydraulically rough boundary. Well, already we have defined that. Then we need to know another fundamental relationship which relate the shear stress tau. We were talking about bed shear stress, which we were writing as tau 0. Well, but there may be a situation that we need to know the bed shear stress, but exactly at bed what is happening it may not be possible, and sometimes our say boundary material or the bed material size is little larger, or say we need to actually consider, say if it is the bed, then say boundary materials are actually like this, and then we need to consider shear stress to move this particle. Shear stress is acting at this surface. So, it is not really acting at this point, but it is acting at some height. That height is nothing but equal to the diameter of that particle. So, that way we need to consider those things, and for understanding all those we need to know this Prandtl-von Karman universal velocity distribution equation. Well, now say we need to start from one relation that we call as a Prandtl turbulent mixing length theory. Well, we will not go into much detail of these things, how it is coming, but we will start with taking this expression as it is, that is, if A in a channel, say this is the surface, and then this velocity distribution we are interested, how this is actually velocity distribution is occurring, and very near to bed, say at any level here, at any level. So, the u is changing, and at depth y, say rate of change of this is du dy, du dy. So, rate of change of velocity with respect to y, we are just writing like this, and then shear stress at any level. This is, we are not mentioning this shear stress to be the shear stress at the bed. It is valid, the shear stress at any level can be expressed as, so shear stress at any level is equal to rho, that is the density of the fluid, then k square, this constant is called von Karman's constant, and then it is y square, means k square, y square is the depth from the bed, y square, and du dy whole square. So, that expression we are taking directly, and von Karman found that after experimenting in this particular phenomenon, he found that this k can be expressed as a constant value. This k can be expressed as a constant value. That value he suggested is 0.4. However, this nowadays we can say that the k we cannot actually consider as 0.4, it will be influenced by several other parameter. Anyway, right at this moment we are considering that k to be constant, and let me take as k as 0.4. And then how we will consider the shear stress at very near to the bed. This is our bed. So, shear stress at bed, if we assuming that shear stress near the boundary as equal to tau 0, means tau 0 is basically bed shear stress, and our interest is to have some expression for tau 0, and if that shear stress we consider that very near to bed is, we are considering as tau 0, that is the shear stress. Okay. With that if we start, then we can ultimately derive an expression for velocity distribution, and that velocity distribution expression will be finding that u can be expressed in term of logarithmic equation, and that is why that we term as logarithmic velocity distribution equation. Well, you can concentrate into the slide that as now we are talking about bed shear, and we are writing say tau 0. Well, we can write a small diagram here also, that this is the bed, and we are writing this as tau 0. Tau 0 is equal to rho k square y square into du dy whole square, du dy whole square. Then we know that tau 0 by rho, already we have expressed this root over this is equal to, we can write k y then du dy, k y du dy. Well, now tau 0 by or rho, that we can write as shear velocity u star, and this is equal to k y du dy. Now we are in a position that we can separate the variable and we can integrate it. So, we can from here we can write that 1 by u star into du is equal to 1 by k 1 by y into dy. Okay. Then integrating this what we can get, this will be u by u star u by u star. So, u is the velocity at any point, we are getting integration of du and u star is remaining here. This is equal to 1 by k, then this will become log of y, 1 by k, and then we are getting log of y and plus say c, log of y plus c. Okay. This is say c dash, I am writing this c dash as a constant of integration. Well, now from this we need to find out what this value of c and how we can write this. In fact, this from this integration we are almost getting a relation that if we try to know what the velocity u at any depth, we can find with respect to y. But and then here we have the von Karman constant, that value also we can take as 0.4. But what this constant of integration that will be? So, that we can find from the boundary condition, that if for say y equal to, let a very small distance c, at y equal to c, say u is equal to 0. So, u will become somewhere 0. If I draw the velocity diagram, y will become somewhere 0, but very near to the bed, say at y equal to c, u is equal to 0. So, with that if I write, then we will be getting that from the boundary condition 0 is equal to say 1 by k log of c is equal to plus c dash. So, we can write that c dash is equal to minus 1 by k log of c. So, finally, we can write u by u star is equal to 1 by k, then log of y, and c, in place of c dash we can write minus 1 by k log of c. Well, then this we can write that u by u star is equal to 1 by k log of y by c. Well, so this is one relation we are getting. Well, now we know that this 1 by k we can express, k we can write as 0.4, and this logarithmic actually it is e base. So, we can write from this expression, let me write in take a fresh space, you can write u by u star, that we can write as 1 by k I can write as 2.5. 1 by k can be written as 2.5, and then it is log e y by c. Then if we convert it to log 10, then we can write u by u star is equal to 2.5 into 2.3, converting it to 10 base. So, 10 y by c. So, that will give us ultimately u by u star is equal to this. If we combine, then we are getting 5.75 log of 10 y by c. Well, this equation is in the logarithmic form, and of course, we are having problem with this c value, again that we need to find experimentally, otherwise this equation we can call as logarithmic equation. Then for smooth boundary, that is why we were discussing what is smooth and what is rough, to get a complete expression for this equation. Now, for smooth boundary means we are talking about hydraulically smooth boundary. Again, for smooth boundary, von Karman he conducted experiment, and on the basis of his data he could get that c can be expressed as this c can be expressed as nu by 9u star. Now, if we put this value of c, then we can write it in the form that u by u star is equal to 5.75, then log of 10, and this 1 by c. So, it will be 9 we will be writing separately. So, it will be say u star y by nu, then of course we can write plus 5.75 into log of 9, we are writing separately in this. Okay. Now this u star y means y is what? Y is the depth at any point, y is depth at any point, we are talking about a depth at any point y. So, at any depth y, when we are having that we want to find the velocity u at any depth y, then we can find out this u, do not confuse, this is not u star. So, okay. We want to find this u, so u we can find in terms of y. Of course, for that we need to know this shear velocity u star, and to know this shear velocity we need to know rho, density of water, of course we will be knowing, but we need to know the shear stress tau 0. So, once we know the tau 0, we can find it and we can have this equation, and u by u star, of course we have a different name for this expression, 7.5 log of 10 base, this u star, let me write this u star y right now, and then nu, and then plus this value, if we simplify, it is coming as 5.5. Okay. Well, that means these are constant, all u star y by nu. We know that what is the expression for Reynolds number? Expression for Reynolds number is u v, that means velocity at a particular point. If we try to calculate the Reynolds number, we know that u v by nu, nu is the kinematic viscosity. Well, here nu is kinematic viscosity, nu is kinematic viscosity. So, as we know that u star, or say u y by nu is the expression for Reynolds number. But here our this velocity is not the velocity that we are having at a particular point or something like that. It is called shear velocity. So, this Reynolds number is also called shear Reynolds number, and that is why we can write it in the form that u by u star is a function of, that means all this we can just club as function of u star y by nu, u star y by nu. So, this is one important expression that we will be using in our subsequent analysis. Then this is what we are doing. One point we are knowing that, see, till now we are expressing tau 0 as some value root over u star as root over tau 0 by rho, and tau 0 we got one expression that w r s. If we remember, just now we did that, tau 0 is equal to w means unit weight, sometimes we can write it as gamma also. So, gamma r s. Now, all these things are applicable when it is a case of uniform flow, as we did cancel all these things. Even if we apply it to some other cases, we will have to make it very small, we have to discretize it, and we need to consider that this part is smooth, and that way only we can express that things well. So, understanding of these things are required. Now, this, if it is not a smooth boundary, then also we have an expression for this C. That also let us keep, that is, if it is not a smooth boundary, for rough boundary, of course that may not be coming right now into our application in deriving under subsequent relation, but still as information we can do that in terms of Nikuratz's experiment, again that sand grain roughness Ks, in terms of sand grain roughness Ks, C can be given as Ks by 30, and using that, if we go for this expression, then we will be getting u by u star, that means replacing C value by Ks by 30, we will be getting 5.75 log of 10, then it is y by Ks, plus 8.5. So, that means this here for rough boundary, our velocity distribution is not dependent on the Reynolds number, rather it is depending on the depth and the roughness, this ratio, this value. So, that way these things are this information should be useful. And for, of course, this is we are talking about that rough boundary and smooth boundary. If the boundary is in transition, then also in different books, in the books of Rangaraju, K.G. Rangaraju also he has given that is experiments, compiling the experimentation done by different people at different time. He gave that value, that this particular value can be changed as C1 and I mean some constant, and for transition means again this transition depends on the ratio, how much is the ratio Ks by delta. So, depending on different value of Ks by delta, and he gave some value of this parameter, say C1, some coefficients, and then for that can be used for transition boundary also. Well, now with these informations, now we can proceed further. Well, so till now what we are knowing is that when a fluid is moving, then it is exerting some stress at the bed, rather we will call this as a boundary. At the boundary it is exerting some stress, and that stress we know that this can be expressed as if we write it as tau 0, then we get a shear velocity u star, and then that stress if it exceeds a particular limit, then there will be erosion. And then considering that erosion means that again we use a concept that is called as incipient motion condition. That means the force required to take the particle, or say velocity required to move the particle is one issue, and then the particle has its own weight. So, it will be having its own resistance, it will try to stand in its position. Now, when the force or the velocity is just sufficient to move the particle, then particle is just in the verge of motion, So, that situation we call as incipient motion condition. Well, now for deriving a relationship for this incipient motion condition, there are different approaches, or different approaches are possible. Well, one approach is called that competent velocity, and based on this approach also we derive some relationship. Competent velocity means we talk about a velocity, and one point we should always remember that because the sediment movement, these are very complex. It is not that straight simple like the rigid boundary channel, and because the reason is that the sediment what we are talking about, say in a bed, although we give a particular size of sediment, in nature we cannot have that uniform size of sediment. It will be mixture of various sizes of sediment, and sometimes we talk that only frictional resistance between the sediments are existing, that is to move the sediment from its position, say frictional resistance between two sediments are working, and then that is why, or sometimes its weight is only responsible, this is moving. Suppose if some force is more than that weight, it can be moved. But sometimes in sediment there can be finer material as fine as clay, and that way there can be some cohesive force between the sediment also. So, or as a whole in the sediment we can have say cohesive force. Well, by sediment we are including here say boulders, also small boulders, or pebbles, or say very fine sand to very coarse sand to fine sand, all these we are including. And most of the study generally considered that sediment to be cohesionless, and that way some expressions are derived. And so, these expressions, there are a lot of assumption always. Well, and then so when there are a lot of assumption, exact analytical solution or exact analytical expression of a particular value is not possible. I mean, if we go by some analytical approach, there will be lot of assumption, and what will be derived ultimately, that may not be giving us exact result. So generally recourses are made to experimentation. Lot of laboratory experiment has been conducted already by different scientists all over the world at different places. And then similarly, again there is another point, that is the experimentation that is conducted in the laboratory is done in a small scale. I mean, you cannot represent a river exactly as it is, you will have to reduce the scale, and that scale when we reduce, then but the sediment size, if we reduce to that particular in the same scale, suppose a 100 meter wide channel we are representing by a 1 meter width channel, then the scale is 1:100. Now there are some sediments are flowing in the river. If we need to reduce it, the sediment size, this will be very small. If we reduce it to 1:100 scale, that will be powder, and this behavior will completely change. So we cannot do that, because it will become completely cohesive in that case if we reduce it to that size. So that a lot of complexities are there in experimentation also. But still, with our knowledge of hydraulic model, that hydraulic model study, that will be taking up as a different topic in our later part of this course, hydraulic engineering, and there we will be discussing all those things in detail. But what I want to emphasize at this point, that this sort of analysis on sediment are really very complex. We normally we always need to go for experimentation, and apart from the experimentation, as there are difficulties in experimentation also, from the understanding what we derived in experimentation, we need to observe in the real field also. So observation in the real field also are necessary, and considering all these things, some theory has been developed, and using those theory for our engineering purpose, we have seen that being little conservative, remaining in safer side, we can always design our structure. Of course, the scouring and all these things are still a active research area. We are yet to come out with a very concrete decision about this sort of scouring in many cases. Well, and then say what we were discussing is that there can be different approaches for having some analytical understanding of incipient motion condition, and one is competent velocity approach. There we make an assumption, or we take it like that there will be a competent velocity, which will be just sufficient, to remove or to move the sediment particle in the bed. So that velocity we can express somehow, and we can get a relation. But another approach is the critical force approach. You can call it as a critical force approach or competent force. So there will be a force which will be sufficient, just sufficient to move the particle from its position, and then we will try to equate the force required to move that particle, and then what is the actually force exerted by the flow on that particle. There are two things. One is the force when the fluid is moving, it will be exerting some force, and then we need to see that that force when it is just exactly equal to the force required to move the particle, or just little more than that force, then the particle will start moving. We will be getting an incipient motion condition. Again, when we talk about force, there can be two concepts. One is that lift concept, another is that drag concept. Well, lift concept means we know that when a fluid is there, some object is moving into the fluid, or fluid is moving around the object, there will be lift force acting on the particle and drag force acting on the particle. Well, now in to move the particle, both the force can be significant, and that way sometimes we consider it from the, that means it can be considered that lift force we can consider, or sometimes we can consider drag force. But in this sort of analysis, when we talk about open channel hydraulics, then the particle will be in the bed, it is resting on the bed, and it is found that when the flow is moving over that particle, drag force will be significant, drag force will be significant, and that way generally this drag force approach is adopted. Generally this drag force approach is adopted, and that leads us to a term that is called critical tractive force, that is called critical tractive force. So, we will be discussing that how this critical tractive force we can express, and using this critical tractive force how we can find that how much sediment will be moved in a bed, and this flow will be different from the flow in a rigid boundary channel, or if that critical tractive force is below particular value, then we can consider this as a as similar as that of a rigid boundary channel. Well, then sealed, this is a very popular name in the sediment field, that is Seals. He gave a semi-theoretical analysis for computing critical tractive force. He gave a semi-empirical, semi-theoretical rather. Why? Because in his analysis, he initially came with the understanding of various forces, and he equated these different forces, and there the theoretical basis is there. But when the theoretical forces were equated, then in fact to express this force directly it was not possible, because the sediment sizes are different. Suppose we want to know how much force will be required for lifting or for dragging that particle, then it will depend on the weight of the particle. Now, when we talk that weight of an individual particle, then we need to know what is the volume of that particle. Now, in a bed, the particle will not be exactly sphere shape, it will be of different type, different shape. So, to find out what should be the volume of that particle, we need to make some assumption there. Say, based on the shape of the particle, volume we can consider that it will be proportionate to the diameter cube. If the diameter of the particle is d, then we can call it is proportionate to the diameter cube. However, exactly how much, it is not possible. So, that way he, by his analytical understanding, he derived the relation that this can be equal to these things, this value can be related. Then these he collected lot of data, conducted lot of experiment and collected lot of data, and those data were used to relate this sort of parameter. Parameters means the parameters for which he has now the analytical understanding that these are related, or this can be related. This is one is function of the other. So, that way some non-dimensional parameters were related, and then some graphs were plotted, and then from that critical tractive stress, what it can be, that was analyzed. Of course, later on some other scientist has also done on that direction and has modified his analysis, or rather his data, and has given some other value, of course more or less close to the value what was given by Sealed. Well, so that we will be discussing in our next class, that how Sealed theory can be used, and then based on the Sealed theory we will be having an understanding what sort of shear stress will be sufficient to make the particle moving, and if the particle start moving, then we will need to know that how the bed form will change, how the bed form will change. And then the question coming, if the bed form change, then how the resistance value, that is we were using Manning sand for resistance parameter, whether that will be valid, or we need to take some more special understanding or some more correction to this value. Well, that we will be discussing in the next class. Thank you very much.